continuing today with curvilinear motion, we introduce a new coordinate system of normal and tangential components. And so we start out by defining our two unit vectors, and as you can see here, the tangential unit vector, of course, is going to be tangent to the curve, and the normal vector is going to be toward the center of curvature. And unlike the I and j that we used in the rectangular components, these vectors are going to change with time, so we have to find the derivatives of the velocity and acceleration. We're going to have to also take derivatives of these two unit vectors. And we do that in class, but we won't repeat that here. One thing we know for sure is that the direction of the velocity is tangent to the path, and so we can simply write it as the speed times the unit vector in the tangential direction gives us the velocity. For acceleration, we're going to have two components. The tangential acceleration is just going to be v dot, in other words, just the change in speed. So if we're going at a constant speed, the tangential acceleration will be 0. However, if we're going around a curve, we're still going to have a normal acceleration, and that normal acceleration turns out to be the velocity squared divided by rho, where rho is the radius of curvature at any point on the curve. So our acceleration we can write again as v dot in the tangential direction plus v squared over rho in the normal direction. And as we noted earlier, speed may be constant, but that doesn't mean the acceleration is 0. It means the tangential acceleration is 0. But again, as long as we're going around a curve, we're going to have a non-zero acceleration. And of course, to find the magnitude of acceleration, we just take the sum of the squares of the components. Now, in many cases, we're going to be given the curvature, the curve that we're following is going to be given by an equation. And so something that you might have learned in calculus is to find the radius of curvature at any point. We do that with the first and second derivatives of y with respect to x. So that definition of the curve lets us define what the radius of curvature is at any point. So here's an example problem. We've got a car going around a highway curve. That highway curve has a radius of r, so that would be the radius of curvature. If the speed's constant, then the tangential acceleration is 0. If the speed is changing, then the rate at which it changes, again, is the tangential acceleration. And we calculate the normal acceleration as simply v squared over r. So pretty straightforward. And if we're going around a curve that's defined by an equation, like the problem here, pretty much follow the same steps, only we'll have to find the radius of curvature from that equation. So next time we'll use our third coordinate system, and that is cylindrical coordinates. If it's a 2D problem, of course, that just becomes polar coordinates. So one place where that is useful is rotating machinery, where instead of being given the velocity of a particle, you might be given the angular velocity, such as a shaft's turning at so many RPMs.